Thank you for the introduction, and I'm very excited to share with you today the insights I gained in this project. This project was about segmentation of 3D metal objects of cone-beam CT in the cone-beam CT volume, and we were putting a focus on doing that by also including projection domain information, with the final goal of applying it to metal artifact reduction algorithms through inpainting. I investigated this project in cooperation with Siemens and the Pattern Recognition Lab under the supervision of Bjoern, Kreher, and Andreas Maier. I would like to motivate this, as the previous talk, with an image from spine surgery. This time it's not catheteries. On the left-hand side here, you can see a reconstruction without metal in the field of view. And you can clearly see the clinically important landmarks like a bony outline around the nervous channel, whereas on the right-hand side here, the metal artifacts obstruct this clinically important information. And the cone-beam CT systems are primarily used for CT with 2D imaging capabilities for guidance during the surgery, and the 3D scan is often conducted at the end of the surgery to validate these positions. So these artifacts are a huge problem for the effectiveness of the systems. Luckily, there are methods to reduce these artifacts, and I just want to touch briefly on how an inpainting-based metal artifact reduction works. As the two primary outputs of the C-arm system, we obtain the rotational data, the projection domain images, plus the reconstructed volume with all of the metal artifacts that we observe. In the first step of the pipeline, a 3D metal segmentation takes place from the artifact corrupted volume. And typically right now, this is done via some kind of thresholding approach. As a second step, this 3D metal mask is projected forward in order to yield projection domain traces of this metal, which are then inpainted, and the contribution to the image is removed. If you reconstruct those projection images, you obtain a volume, a reconstruction volume without any metal, and also then without the metal artifacts. The final step in this pipeline is to combine the information from this metal artifact-free volume with the 3D segmentation to obtain a volume that has all of the properties we want. If we examine this pipeline more closely, we can see a clear dependence on this first initial step. So if the 3D metal segmentation fails, the rest of the pipeline will also suffer. And to see an example how the pipeline suffers if the segmentation fails, we can compare these two images. So on the left-hand side here, you can see an example without metal artifact reduction. And you see clearly the metal artifacts that we discussed, whereas on the right-hand side, frequency split MAR is applied using a thresholding-based mask. And clearly we can see that these results are misleading because the center of the screw is not there anymore. And also there's additional streaks originating from that view that were not there and not present in the original image. So all this is to say that we really need a better metal segmentation, and that's exactly the goal of this project. In this project, we compared 3 different methods on the task of obtaining a high detailed 3D metal mask. The first one is, as a baseline, a thresholding-based approach, which only considers the pixel values and the voxel values. The second approach is a bit more sophisticated, and it is applying a convolutional neural network, in this case, a 3D UNet to the artifact corrupted volume. So both methods 1 and 2 consume the volume and try to estimate the metal mask. Whereas the third method is the one I'm most excited about, and that actually tries to incorporate the stack of projection images which don't feature any artifacts. As methods 2 and 3 are supervised learning methods, we have requirements for our training data. And that is that the training data has to exhibit all of these physical artifacts that are responsible for the emergence of metal artifacts, which are beam hardening, photon starvation, noise, and scatter. Let's have a very brief look at how we generate training data that features these physical effects. And in summary, this is something we've heard about today very often. So we use the same kind of forward model that you would also use for material decomposition. In an initial step, we take a cone-beam CT volume and we threshold it to obtain material masks, which are then forward projected and weighted together according to weighted with their attenuation coefficients and a chosen spectrum to yield deep digitally reconstructed radiographs. If we reconstruct these radiographs, we obtain volumes that feature the desired artifacts that should be featured in our training data. The corresponding ground truth mask can be obtained by locating and voxelizing a volume with the same resolution of the metal masks. These are this is one exemplary slice from our training data. And the most important takeaway here is that if you threshold this chromium CT volume, the metal artifacts result in a segmentation where the insides of the screw vanish for the rest of the screw vanishes. That's due to the cupping artifact. So that's just a brief, self-check that our training data features the artifacts that we want. Using this pipeline, we generate a simulation data set, which comprises in total 12 chromium CT volumes from a human spine cadaver study from the lumbar and thoracic region, because we want to focus on that because of pedicle screws. These 11 chromium CT volumes are equipped with manually composed tool configurations. And as a data augmentation step, we rotate these volumes and the corresponding metal configurations in 3D to boost our data set size to 44 samples. Noise and scatter are also really important to simulate, and we take care of that by integrating that during the training as an online augmentation with varying levels of noise. I want to briefly introduce the three methods that I would be comparing. The first one is called optimal thresholding, because we apply, so I think it's very evident what this is about. We apply a threshold to the image and we select the threshold that yields the highest dice coefficient when we compare the resulting segmentation with the underlying ground truth. So in this case, it would be at the very tip of this curve here. The second method is the reconstruction domain convolutional network. And as I introduced earlier, the reasoning here is that, or the intuition is that spatial features will greatly improve the segmentation. To implement this, we use a method called no new unit, because that's a paper by the DKFZ, and it offers to automatically configure and train a unit architecture by something they call the dataset fingerprint. So it takes care of configuring all of the hyperparameters and patching and whatnot. So for our dataset fingerprint, it's decided to use patches of 128 pixels volume size. And we actually decided only to train the 3D low-res model, because later on in our project, we only compare it to downsampled data anyway, because full resolution samples wouldn't work with the third method. The results you will see later are also evaluated using five-fold cross-validation. Finally, let's come to the cross-domain learning. And the intuition here is, as teased earlier, is we want to enable the model to have a look at the data which has not yet experienced any artifacts. So on the left-hand side here, we see the raw projection images we get from the system in the line integral representation. And the first three green dots here, or lines here, represent convolutional layers that the model can apply to the projection domain images. Then in the middle, we have a back projection operator, and on the right side, there are some computations on the reconstruction domain side. To enable this kind of model, we obviously need a back projector that is derivable, such that we can train this model in an end-to-end fashion. Here, it's important to understand how gradient backpropagation works, and I will just introduce this for the folks that are not so involved with deep learning. So during deep learning, you have to propagate an error back through the network, and a volume error delta E here will be distributed to all those pixels in the projection data that contribute to that voxel, right? So this is how we can train the projection domain side of the model just by feeding it volumetric masks. This is the resulting final architecture of the cross-domain unit. So as the name says, it kind of looks like a unit with an encoder side on the left side in green in the projection domain, and the decoder side, so the deflating of the information, in the reconstruction domain. In the middle, you can see the back projection operators that are placed on the skip connections, such that the reconstructions are fed into the encoder part on the right side. So this illustrates the different resolutions that the network works on. So it has different levels of scale. In the topmost connecting skip connections, we use half of the available detector resolutions, so 488 by 488, and we reconstruct volumes of half of the available volume size as well. During one forward pass of this model, we actually have to evaluate the back projection operator 84 times. So 4 times at the first stage, 16 times at the second, 32 at the both last stages. This method had to be trained with a batch size of 1, just because the GPU would overflow with larger sizes, and we use the Atom optimizer to compensate the resulting stochastic gradient updates that we get from that. And the results we see are also evaluated using 5-fold cross-validation on our simulation data set. These are the quantitative results, comparing the 3 methods on the simulation data set. Kind of as expected, we see that the thresholding method struggles with some of the samples, but there are also cases where a thresholding-based approach is totally reasonable. I would hypothesize that those are the samples with very few metal artifacts. Comparing the 2 other methods, we see that they perform fairly similar with 0.86 and 0.87 mean average dice coefficient. I wouldn't read too much into the tiny differences in the standard deviation. What's important, however, are some other attributes of those methods, and that is that that NN unit, so the 3D unit, uses a lot of pre-processing like patching and so on, and that therefore it takes almost 45 seconds to predict one volume, which is too long in a clinical workflow. So our model would be, 10 times faster. Also, the 3D unit has way more parameters, so it's a way more potent model as it has 6 million parameters. Our model is kind of limited by the GPU size at the moment. So it only has around 200,000 parameters, and analogously, the training times are way longer for the 3D unit, with almost 100 hours for the training. So our smaller model converts in only 16 hours. And yeah, this I have explained a lot by now. So our model is clearly bound by GPU memory. I want to have a look at some qualitative results that you get a feeling for what these dice coefficients actually mean. The ground truth we can see here on the left, and the inner part here on the screw is actually a cannulation, so the ground truth is not wrong or anything. This is a very fine detail that we would have loved the models to come up with, but as we can see, none of them got it, except maybe for the thresholding-based method, but we can see that it neglects the entire inner part of the screw, which is, as introduced earlier, due to the cupping artifact in 3D. A more detailed look at the segmentations of both learning-based models doesn't reveal much difference, I would say. So, and I would be cautious to read in too much, comparison between those two, because as I said, we work on downsampled data as well. Yes, what's way more interesting, in my opinion, is trying to throw this model on real data for now. And so I did that with 4 different test examples from our measured data set from the same spine cadaver study. And in the top row here, we see the volumetric, the 3D unit, and we can see that it has a decent generalization to these measured data sets. All of the screws are segmented pretty clearly. However, our method displays a lot of false positives, which surface as a halo towards the bottom of the image. Yeah, just an observation. So let's get to the question why I think that is. And I see 2 problems that are now evident to me. The first one would be our training data simulation feature. Okay, let me rephrase that. As our generation of training data is derived from only one volume with 16 centimeters side length, the Chromium CT volume, the projection data we obtain from that can only contain information from within that volume, right? So something like the second knee, as you can see here on the bottom, would never be seen by the model during training. However, they could be seen from measured data. And the second problem that I see is the one that I suspect these halo-like artifacts come from is truncation, or to be more clearly, the truncation-induced problems with the Ramlack filter that has a jump because it's a periodic signal, and both of the edges at the side of the volume don't line up. With truncation correction, however, which is what the 3D unit sees, there's no such problem. And that's why I think the unit generalizes way better to unseen measured data. As a kind of an outlook, or going back to our motivation, I want to compare the effect that these segmentation masks using the CNN in 3D, the ones that generalize well, have on the MAR method, on the frequency split MAR. So in the reconstruction without any MAR, we can see a lot of metal artifacts, whereas in the middle with the frequency split MAR with standard thresholding as it is implemented in the product today, large parts of the screw are apparently not segmented and thus the artifacts are not reduced. However, if we plug in the segmentations we get from the 3D unit, and we get quite clearly reduced artifacts. And yeah, this is just a cherry-picked example to visualize the effects on the method. So let me conclude this talk. In the course of this project, we have evaluated 3 different methods on the topic of metal segmentation. One clear takeaway is that structural features clearly help to, segment metal in 3D. The 3D unit we've tested out using NN unit on direct segmentation from artifact corrupted volumes yields a pretty good dice coefficient or average dice coefficient on our simulation data set. However, it has a pretty long inference time of almost 45 seconds, which we aim to reduce in the future. Our cross-domain unit, which is an idea that I find very cool, features derivable back projection operators on the skip connections and thus enables end-to-end training. It yields 8.867 dice coefficient on the 5-fold cross-validation with a very short inference time. As an outlook, I would definitely propose to improve the generalization of our cross-domain method, tackling the 2 problems that remain with it. And also Tristan is actually at the moment evaluating the impact of these better masks on the success of metal artifact reduction algorithms. With that, I would be at the end of my talk and would love to accept questions.
Thank you, Maximilian. Questions? Yes, Josh.
Hi. Really nice talk. I just want to understand on your cross-domain, the inference is done just on the projections, right? So a first pass reconstruction is not necessary.
Exactly.
Yeah, so that's a big advantage. On the, just a question in terms of the inference on the volume taking a long time. Are you inputting the entire volume into your unit or just a section of the volume with the metal in it?
Yeah.
Just wondering why inference takes so long.
Yes, exactly. So it takes so long because this method works on patches of the volume. So the full resolution volume is chopped up into sub-volumes, which are then individually predicted and then stitched together back in the, and actually in the implementation of this training that I use, I guess there's a bunch of pre-processing steps like random flips and so on of the sub-volume to increase model performance. So I would have to have a deeper look at how you could cut the inference time, which I'm sure is possible somehow.
Yeah. Okay. Thanks.
Kind of in a similar question. So your 3D unit implementation has a greatly larger number of trainable parameters than your cross domain. Did you look to see what would happen if you just had a skinnier 3D unit in the volume domain, right? Because like that would presumably have a similar influence performance.
Yes.
And like there'll be some point of diminishing returns with network complexity.
It's a very good question. So the very distinguishing fact or difference between metal segmentation and any other kind of segmentation like organ segmentation is we have a strong prior, and that is, the value. So just based on the value, we should be able to obtain a pretty okay prior segmentation kind of. So I totally agree with you that if less complex model in the reconstruction domain should be totally possible. Yeah. Doesn't have to be a full blown.
Thank you for your presentation. I was wondering, so one of the main reasons to not use image-based segmentation with metal artifacts is for the case that the metal is outside of the field of view. Do you think that your method would also work for those cases?
Yeah, so that was also one of the motivations why we decided initially to look at projection domain segmentation. However, what we're doing now is not projection domain segmentation, but 3D segmentation based on projections. So using the method as it is implemented now or thought of as of now, it wouldn't be possible because we're only able to reconstruct metal that's within the volume that we also reconstruct within the method, right? So if the metal is outside of the volume, we wouldn't catch it.
Okay, thank you.
Yeah, hi. Thanks for the talk. As we already discussed, I'm not really into deep learning stuff, so this might be a very naive question. Right now, you've given the example of segmentation of the screws, which is just a distinct shape. Is the network only trained for screws or also for like other types of metal implants?
No, it's trained on a, I skipped that, yeah. So it's trained on a variety of different tools. Actually, we have a lot of meshes available from Novasive that it's predominantly spine surgery meshes. So there's also, as you can see here in this image, towers and tulips and all kinds of fancy surgical equipment in there. Yeah.
Yeah, you toward the end, you speculate there are two major reasons leading to the artifacts in the X domain approach. Did you do a simulation study to test out? Can you?
You mean this?
Yeah, the two problems you speculate. Just curious.
So just by the look of these results here and these huge false positives in the bottom area, I'm very certain that it's originating from this truncation artifact like this. Yeah, and we're currently investigating methods to, yeah, was that your question? Yeah.
That's okay.
Yeah, so
Thank you.
I really think if you're able to circumvent that problem by adapting the RAM-like filter that's currently implemented in the model, that should do enough.
All right.
But I would have
you.
to test it out. Yeah.
Yeah. Thank you, Maximilian.
Yes.
All right. I'm going to give the mic to Bjoern.